And again, we're working on chapter 4, just getting started with that. And big picture idea is that we want to start looking at these questions of, it's a process called optimization. And if you ask calc students in general, they'll say this is one of the hardest topic, if not the hardest topic they learn. So we're spending several days on it. And what we're doing is we're building the groundwork for how we can use derivatives to help us create this logical framework we can use to find optimal values, find the biggest, find the fastest, find the slowest, find the cheapest, these type of EST words. So we're doing this from a strictly, here's a function, how do we find the biggest and smallest values? And then we're going to leverage that into, here's a real world situation. How do we take this real world situation? How do we create a model of the situation? And then how do we use that model to do the mathematics, the calculus to find the optimal values? And I think the modeling part is probably the most challenging for students because we're basically asking you to synthesize everything you've ever learned about mathematics and put it into one problem. So if you have any spare time this weekend, dig out any cheat sheets or study guides you have from geometry, like what's the volume of a sphere? If you can't write that down right now, maybe make a list of like volume of a cylinder, a sphere, a cone. Make sure you get those geometric formulas. What's the area of a triangle, the area of a square, like the area of some of these common shapes. Do you remember anything from geometry about similar triangles, Pythagorean theorem, that sort of thing? Basic trig relationships, sine is opposite over adjacent. Any of those formulas you have, if you want to maybe gather those review materials in one place, we'll be using a lot of those next week. Okay, another thing that you're going to have rock solid before this unit is computing derivatives, understanding derivatives graphically, interpreting them as slopes of tangent lines, understanding concavity, increase, decrease, that type of thing. So those are all pieces we're going to be needing. They'll be thrown together. So let's dig into this. Quick review, we talked about local maxes and local mins. And remember, we have this idea of local as kind of like nearby. So we might say, within the state of Colorado, what's the tallest mountain? And then if we change what local means, we might say, within the contiguous United States, what's the tallest mountain? And so if we change that boundary, does that change the answer? Okay, so local to the state of Colorado, the highest point is Mount Elbert. But if we increase the boundary, increase our local, make it larger, then we have a taller mountain someplace else. And if we go to the entire world, then we have a taller mountain someplace else. So a global max would be like on the entire function. A local max would just be nearby. So for example, I'll circle these 2 points here. These are both maximum values. Technically, they're both local maximum values, but only one of them is a global maximum value. So they're both local. Because if you restrict the domain to kind of the parts of the graph that I've circled, though there is one output that's bigger than all the nearby outputs. But this one up here is also a global maximum. So global or absolute, those are words that refer to on the entire domain. It's the highest x value. Well, yeah, it's the x value that is greater than or equal to all x values nearby, right? We want to get that equality. Because what if the function had done something like this? There's still only one global max. The global max is 1, but it reaches it at 2 different x values. Okay, so yes, the global max is the output that is larger than or equal to all other outputs on the entire domain. Whereas locally, it's an output that is larger than or equal to nearby outputs on a subset of the domain. And then we have the analogous thing with minimum. Does this graph have a global minimum? If so, let me know in the chat window. Does this graph have a global minimum? Just give me one number that's the global minimum. What is the global minimum? Let me know in the chat window. And I want global, which is the absolute smallest output. Okay. And when I want the if I say I want the minimum, I want the output value, not where it happens. So yeah, somebody was safe and they put, oh, the minimum is -8 when X is 5. Great. That's the safe way to give the answer. But if I really just want the minimum value, all I want is -8. So make sure that you get the concept and double check how the question is phrased to give the right answer. Okay. So yes, the global minimum is down here. And I guess I'm kind of just circling the point. So actually the global minimum is technically -8. And the global max is technically 1. But they are happening on the function at these coordinate points. So try to tease out your inputs and outputs. It's tricky to do. Okay. Boring. I don't like critical points, but that's okay. We'll get to them. Now, where are the local minima? I haven't circled everything exciting on this graph, and I should have picked different colors, but we have a minimum value here. And if we look at endpoints, we have a minimum value there. Okay, for all the points that I've circled, all the maxes and mins, let's think about the derivative at those points. But first is a question in the chat window. You can give an ordered pair notation for answering the max or min, unless the question is like, what's the maximum profit? And then you probably just want to give the dollars. Like you just want to give the question that's like, if you have to sell 25 rocking chairs to maximize your profit, you don't want to say 25 comma 10 million or whatever. I'm just making up random numbers here, right? Just the profit would be the 10 million, and if they ask you how many rocking chairs, then you'd say the 25. So if it's a word problem, then really pay attention. If it's more general, like in class conversation, the ordered pair is a great way to go. Okay, talk about the derivative. Let me know about the derivative. Let's start naming these points here. What is the derivative when x is equal to 2? What's the derivative when x is equal to 3, 4? And notice these places are where I've circled. Yeah, be careful about 2. If we zoom in, this is actually a sharp cusp. So tangent slopes from the left are going to be getting steeper and steeper and steeper, and tangent slopes from the right are going to get steeper and steeper and steeper. But the ones from the left are positive sloped, the ones from the right are negative sloped, and negative infinity does not equal positive infinity. So there is actually no derivative. F prime of 2 does not exist, okay? But F prime of 3 is 0. F prime of 4 is 0. Good. Oh, so here's a good question. What's going on at -2? And same thing, what's going on at 5. So when we talk about derivative, our definition has the limit as h approaches 0, and implicit in that is we're approaching 0 from both sides. So if I'm sitting at -2 and I'm trying to let h approach 0 from both sides, that works okay from the right, but it doesn't work from the left because there's no function there. We don't know what the function's doing. So derivatives at endpoints, it's a little tricky. So side note, you could define a one-sided derivative if you wanted to. Some textbooks do, we are not. We won't bother with this. But in theory, you could define a one-sided derivative. And then you just say, well, it looks like it probably that tangent slope. We basically won't worry about the derivative at an endpoint. Okay. But yeah, so that's a side note on derivatives at endpoints. You can talk about a one-sided derivative. We're going to skip that. Okay. Do we have maximum values on this graph at any places where the derivative is positive or negative? And basically, maybe we should, so coming back to this derivative at an endpoint, we should say that we don't really talk about derivatives at an endpoint. So we might say it doesn't exist at an endpoint because we can't do a two-sided limit. So we can also treat endpoints separately, but think about all the places I have maxes and mins. They're either at endpoints or places where there's something that's true about the derivative. So let's take a step back. Here's my question for you. Can I have a maximum or minimum value when the derivative is positive at that point? Can I have a maximum or minimum value if the derivative is negative at that point? And so one thing to consider might be, let's say that I'm right here, and I know the f prime of this point is negative. And so if I were to nudge, if I were to like give a little wiggle room, I'm standing at that point, I'm standing at x equals, I don't know, 4.72, I don't know what, whatever. If I were to nudge myself a little bit, if I wiggle just a little bit, right? If I'm up here and I look at what happens when I have this wiggle room, if I kind of nudge from side to side, as I move to the right, as my x values increase, my function values decrease. So I'm standing at a point that's taller than nearby points on the one side. And if I look in the other direction, the outputs are actually larger. So when the derivative is negative, if I look left and right, I see points bigger and smaller than where I'm standing. So there cannot be a maximum, no max, if f prime is less than 0, or if f prime is greater than 0. And we're not at an endpoint. Good. So all of the places we have maxes or mins correspond to places where the derivative is 0 or undefined. Now let's be careful. Are all places where a derivative is 0 or undefined guaranteed to give us a max or a min? And if you're saying no, can you provide a counterexample? Specifically on this graph, you could give me an x value of a place we can talk about. Good. Okay, so I guess I should talk to my dog more so my voice warms up before class. Sorry about that. A little scratchy today. Okay, so if we're going to have a maximum value or a minimum value, it's either at an endpoint or a place where the derivative is not positive or not negative. Okay, so what is the same thing of saying, like, I could say the derivative is not negative or not positive. What's the opposite of that? How do I express that in positive language? So I only have a max or min if x is equal to an endpoint, or what can I say about f prime? I want to say not plus, not minus. I don't want the derivative to be positive. I don't want the derivative to be increasing. So what are my other options? Other option. The derivative is 0, or, because don't forget about positive 2, what happens at 2? Yeah, f prime does not exist. Okay, and let's think about this just from a categorical perspective. Think of all the possible numbers or functions we could draw, okay? If we think about functions, they are either increasing or decreasing, or they're flat, or they have a sharp corner. So if we think about the derivative of the function, the derivative is either positive, negative, 0, or undefined. Is there any other option for a derivative to be? We have positive, negative, 0, undefined. Does that cover all possible cases? Is there any other thing a number could be? Positive, negative, 0, or doesn't exist, right? That's everything. So we're going to try to, like, this is a logic process we're going to build, is that we want to categorize all possible outcomes. So think about all possible numbers. They're either 0, they're negative, they're positive, or they don't exist. Think about all numbers that don't exist. That's a good one for the brain today. Let's think about all slopes. The slopes are either positive, negative, 0, or undefined. That might make a little more sense to talk about something undefined when you have a sharp corner. Okay, so if we like categorize all of the slopes as either positive, negative, 0, undefined, that can help us in our reasoning here. Okay, so big take home point number 1, we only have an extreme value. Extreme is the catch-all word for max or min. So if I don't want to say max or min because the Zoom auto transcribe will turn that into Mac sermon. If I don't want to say maximum or minimum, I can say extreme value or extremum. That's just a categorical catch-all phrase there. I only have an extreme value if I'm at an endpoint or the first derivative is 0 or undefined. Now, is it enough to say that all endpoints are maxes and mins? Is it enough to say that all places where the derivative is 0 or undefined give us a max or min? So if the derivative is 0, am I guaranteed to have a maximum? Okay, if the derivative is undefined, am I guaranteed to have a maximum? If I'm at an endpoint, am I guaranteed to have a maximum? Could you think about drawing an endpoint that's not actually a maximum? Okay, so there's the two big things we're going to be building here. We only have maxes and mins if we're at an endpoint or we have 0 slope or undefined slope. But just because we have endpoints or 0 slopes or undefined slopes, that's not enough to guarantee we have a max or min. So how is this actually helpful? Take a look at this graph. If I wanted you to tell me every single x value where the graph is increasing, would you be able to do that? How many x values would you have to give me to tell me all of the x values? Like if I wanted a list, could you make a list of all x values where this function is increasing? There's an infinite number of them, right? If I wanted a list of all places where the derivative is 0, how many places does that happen? How many places have a 0 slope? It's more than 2. It's less than 4. Yeah, it's 3. So yeah, 0, 3, and 4 all have 0 slopes. Okay, so what's easier? Telling me all the places the graph is increasing or telling me all the places where the slope is 0? So if the graph is increasing, I don't care because I don't want to, I'm not going to have a max or minimum there if I want to find that out. But it's not that hard to find out where the slope is 0 or undefined. So basically, here's my function. Here's all these infinite number of x values I have to look at. The only ones that might give me a max or min are the ones that correspond to the derivative being 0 undefined. And that's a relatively small number of points usually. So that's a great place to start the search. So kind of the summary of this circled box here is start your search for extreme values by looking at places where the derivative is 0 or undefined and endpoints. But that second starred point is you have to test these points because not all places give you a max or min. Not all places that satisfy this give you a max or min. So what I do here is I think about this as like start the search. And then the second bullet means test. So those are the two pieces of what we're going to do. We're going to narrow the search, like, well, what are the x values worth looking at? And then once we have a list of x values, then we need to test those x values. And we'll learn several tests over the course of the next week. All right, so just a little bit of closure. I said something earlier about could we have an endpoint where there's no max or min? What if we had an endpoint with an open circle? Okay, and last time we talked about how an open endpoint would not have a maximum or a minimum value because there is no one number that is smaller than all the numbers nearby because of the way the real number line is built up. So I will get that video from Wednesday's class posted soon. So if you're not clear on that, go back and rewatch that conversation. Okay, so the moral of the story is start your search for extreme values by looking at endpoints and places where the first derivative is 0 or undefined. And then you have to test all of those points. So that's the moral of what we've got going on here. What questions do you have for me? So that's a good question. If there was a jump, would there at least be one max min? Jumps could go either way. So you could have a jump with 2 open endpoints, or you could have a filled in point between, or, so the way I drew this picture, if we filled in this value up here, we could have a local max. And maybe have that as open. And if we drew it this way, yeah, it would still give us a local max. But if I changed and I drew this graph kind of coming this way, then we don't have a local max or a local min. So that answer, the jumps depend. You have to take each jump individually and take a look at, is the function increasing or decreasing? And then is the point filled in or not? Yeah, so Jules, the point that you're raising in the chat window is that we're going to do a search for where the derivative is 0, and that's going to give us these points like 0, 3, and 4. And then we have to test all those points to say, oh, when x is 0, we don't have a max or min. So we're going to get some false positives on our first search. Okay, because if I have a formula for my derivative and I just want to know where the thing is 0, then I just set the derivative equal to 0 and solve for x. So we can use some algebra there. Okay, critical points. I think the phrase exists because people got tired of talking, oh, there are places where the derivative is 0 undefined. But they're a little weird to me because there's this requirement that you only have a critical point if that x value is in the domain of the function. So for the example we talked about, all of the places worth looking at are called critical points or endpoints because this function is defined for all the x values. So critical point, it's kind of like if we're going to start our search for derivatives or for maxes and mins, we can look for critical points. And that makes sense because if we have a max or min, then we need the function to be defined there. Okay, so if you're looking for maxes and mins, then you want to look at critical points and endpoints. If we're just looking for a change in increase or decrease, then we want to be like any place the derivative is undefined because the function's undefined might be a point of interest as well. So sometimes I like to just think, instead of thinking critical points, I might like to think points of interest. So it's up to you kind of how you prefer to think about this. You are responsible for knowing that when I ask you, is this thing a critical point? You have to check, is this thing in the domain? So points of interest would be endpoints and places where the derivative is equal to 0 or the derivative does not exist. So points of interest are basically critical points and endpoints, unless there's a situation where the function doesn't exist, because then that's in the place where the derivative would not exist. Okay, so those are your candidates for the maxes and mins values, basically critical points, endpoints. But don't get suckered into thinking critical points means only derivative is 0. Remember that could be derivative does not exist. What questions do you have for me on the definition of critical point? And point can either refer to the x value or the ordered pair, so be careful about that. Critical value is typically reserved for the output, so pay attention to those bits. So definition will be asked some questions about this. This is a good candidate for T1 conversations. I can use definitions. Okay. All right, here we go. Here's another graph. Where are all the critical points? So let's list the critical points and the critical values. Remember, the critical values would be the y value. In the chat window, go ahead and type in an x number if that x value is a critical point. So give me some critical points here. Critical points are places where the derivative is 0 and undefined. What's the smallest critical point on this graph, the most negative? There we go. There we've got a -4. Good. Okay, so we're going to start with -4. Then I think some people listed -3. I think some people listed -1. 0, I think, is a critical point. We got that one in there. I'm going to say this looks like it's 5.5. That looks pretty good, right? Okay, and the critical values would be the corresponding y values. So when at -4, the output's 0, at -3, the output's 1, at -1, the output's -1, at 0, the output is 0, and at 5.5, we're, I don't know, -5.25. maybe. Okay, where are the local minimum values at? So I'm going to go ahead and try to mark all the critical points in, that's way too big, in orange. So critical point, critical point, critical point, critical point, and critical point. And we'll do the minimum values in green. So minimum values, it looks like we've got one at -1 and -5.5. And if we're looking at endpoints, yeah, we want to include -5. Awesome. And let's see, let's do maximum in blue. Actually, yeah, it's okay, that'll work on blue. Maximum values. So we have one at +1 and 0 is slightly larger than anything else, and it's 9. Cool. And notice we had one false, like a false negative there, right? Or false positive. It was a number that came up in our search, but when we look at values on either side, we realized that is not a maximum. Okay. In between two critical points, or let's actually do critical points here. In between two critical points, if the critical points are consecutive, could my function change direction? So think about two consecutive critical points and think, can the function like change direction, be like increasing and then decreasing in between two critical points? So if the function were to change direction, let's say the function increased and then decreased, what happens right there when the function changes from increase to decrease? That would have to be a critical point. So if you have two critical points that are consecutive, there's no critical points in between them, then the function is either increasing or decreasing, but it can't change. Okay, so in between two consecutive critical points, the function is always increasing or always decreasing, but not changing. F is not switching from increase to decrease between critical points. Yes, Nasser, what's your question?
I have a question about -4. I remember on Wednesday, I don't know if it's a different example or something, but I remember you said that it could be a minimum and a maximum when you have a flat, like there's no increasing and decreasing. I don't know if this is the same example or not.
Careful. What has to happen is you have to be flat on a stretch of function. You can't
Oh,
just be flat at a single point. Because
okay, okay.
if we zoomed in like crazy here, that's not what I meant to do. Here we go. Values slightly to the left are going to be slightly smaller, and values slightly to the right are going to be slightly larger.
Yeah, I see. Okay.
So they would not be both a max and a min. But if you have a perfectly horizontal function, then you
For
would
more than
have
one.
mins. Okay, so in between critical points are functions either always increasing or always decreasing. So here we can see we have increase. Between -3 and -1, the function is always decreasing. Between -1 and 0, the function is always increasing. Between 0 and 5.5, the function is always decreasing. And then from 5.5 to 9, the function is increasing. But that's the big idea, is that in between two consecutive critical points, your function can't turn around, because if it did turn around, you'd have another critical point. So when we want to list intervals of increase and decreasing, what we can do is we can make an F prime number line, or an F prime line, or however you want to think about this. And we can put all of our critical points on it. So the critical points are -4, -3, -1, 0, and 5.5. And then we can just ask ourselves, well, what is F prime doing at any X value I want? You can pick your favorite X value in between -4 and -3. So maybe -3.5. Okay. And we can say, oh, well, at -3.5, the tangent slope is positive. So F prime is positive. And therefore, you know your function has to be increasing on that interval. So if you need to find your intervals of increase and decrease, the boundaries of your intervals are going to be critical points. And that works because your function is always increasing or always decreasing in between consecutive critical points. What questions do you have for me about answering 5 and 6? I'm not going to do that here. Are you saying like if you were to graph f prime of x would touch the x-axis at critical points? Well, yeah. So there's two things. Remember, critical points is slope is 0 or undefined. So where the slope is 0, the derivative would cross the x-axis. Okay, so let's look at our maxes and mins here. So the maxes are starred in blue. At every single maximum, what's happening before and after? There is no after at the end point, but what's happening before? So there's a question in the chat window, do we have to find f of x to solve for number 5? In this example, we can do it from the graph, but if you had a function, you could also do that straight from the function. So for this example, no, you don't have to solve for f of 5, you just use the graph. Okay, take a look at every single maximum, and what's the function doing before and after the maximum? Before the maximum, the function is always increasing. And then if we're not at an endpoint, the function is always decreasing afterwards, right? So we could think about a maximum happens. Maximum happens when f changes from increase to decrease, or when f prime changes from positive to negative. Do you have a similar thing for a minimum? Minimum happens when f changes from decreasing to increasing, or when f prime changes from negative to positive. Okay, so if you list your intervals of increase and decrease, and from -3 to -1, we have decreasing. So if I were to write decreasing on here, we see that the function changes from increase to decrease, and an increase to decrease means we have a local max, because the function changed from increase to decrease. So it's not worth looking for maxes and mins unless we're at an endpoint or a critical point. And we can test those critical points by saying, does my function go from increase to decrease to increase, or neither? What's happening at -4? The function's going from increase to increase. There's no change, right? When x is equal to -4, the function's increasing before and increasing after. So do you see how we can use this idea of looking for change and increase and decrease to tell us to test these functions? Start your search for maxes and mins at endpoints in places where the derivative is 0 and undefined. Sorry, 0 or undefined. Look at what happens on either side of those points of interest. Is there a change from increase to decrease or decrease to increase? And then draw your conclusions about whether you have maxes and mins. Okay, so all of that work can translate into writing out a procedure for how to find maxes and mins when all we have is a formula, when we don't have a graph to look at. And we're going to end up with basically 3 tests for testing for extreme values. So the first one we're going to talk about is the first derivative test, because it uses the first derivative, because it uses the idea of like, oh, is my function going from increase to increase, or increase to decrease, or decrease to increase, that type of thing. And we translate that into the derivative. So if the derivative changes from positive to negative around a critical point, then you have a max. If the first derivative changes from negative to positive around a critical point, then you have a min. And if the first derivative doesn't change sign, you're increasing before and after, or you're decreasing before and after, then there is not an extreme value, even though you had a critical point. So questions on the first derivative test, or put a Y in the chat window if you're ready to move on to the steps. Okay, so basically summarizing what we did is you have to find the domain, because that way you know if you have a critical point or not. So you start by finding the domain. And draw an f prime info line. So draw an x-axis, and this is where you're going to summarize all your work, right? You want to know where the domain might not exist, because if you have a place where the domain doesn't exist, you can have a jump. So your function could do something different on one side and the other side. So you want to look at those places. So places where the function doesn't exist would be another point of interest. Candidates for extrema are going to be critical points or endpoints. So maybe if you want to lump all of these points together, you could call them points of interest. So you find all the places it's worth looking at. Check for where the domain doesn't exist, check for critical points, check for endpoints. And then you have to test to see, did we get a false positive? Do we have a place that's not really a max or min? So you do a test. And the one test we've talked about so far is the first derivative test. Okay. And then if you need to know absolute maxes versus local maxes, you can look at the y values. You could use an ordered pair chart, or just look at the y values, look at the output values. The biggest output is your global max, and the smallest output is a global min. And ordered pair just means like x comma y. That's just giving you your x values and your y values. Okay, there's some examples there. You can find lots of examples probably online. I bet Khan Academy does some examples working this out. So I'm not going to do that since we only have 7 minutes of class left. The next thing to talk about is the second derivative test, which relies on concavity. So remember, concavity is curvature. So let's go back to this graph and take a different perspective. Let's take a different look at it. If I wanted to know all the places this graph was increasing and decreasing, I want to know all the places where the derivative is positive or negative. But the easier way to do that is to start by saying, where are all the places the function could possibly change direction? And notice that's basically the same places we want to look for extreme values. The function could likely change direction when we have a max or a min. So if I need to know all of the intervals of increase and decrease, I basically do the same procedure. I find all the places the function could possibly change direction, points of interest, endpoints, critical points, places where the domain, like where x is not in the domain. Okay, and then I can test on each interval to see whether the function's increasing or decreasing. So once I have all my points of interest laid out on an f prime number line, in between two of those points, the function can't change, because if it did change, I'd have another point of interest there. So places where the function is undefined, where the derivative is 0, where the derivative does not exist, and endpoints gives me that those are the points of interest that break the number line up into intervals, where on each interval the function is either increasing or decreasing, but not changing between the two. Give me a thumbs up or a T in the chat window if you feel okay with that. The first derivative, all the points of interest break the interval, break the x-axis into intervals of either increase or decreasing, but not changing. Okay, can we take that exact set of logic and just go up a layer and apply it to the second derivative? So take that exact structure of logic, and now we're going to apply it to the second derivative. So if we're thinking about the second derivative, our points of interest are where the function doesn't exist, where the second derivative is 0, or where the second derivative doesn't exist. That is going to do like an f double prime number line, and that chunks the x-axis into intervals. On each interval there, what can you tell me about the function? What's like the same on that entire interval? What's not changing? So I use the second derivative to break up my number line. What do I know about the function behavior between two consecutive points of interest? The first derivative told me if the function was increasing or decreasing. The second derivative is going to tell me about intervals of concave up and concave down. Good. So all the work I just showed you directly translates to the second derivative. It's the same exact idea. Here's something really annoying. We can't use the phrase critical point to apply to the second derivative. Critical point is very, very, very narrowly defined to be places where the first derivative is 0 or undefined. There is no direct analog to critical point when we're talking about the second derivative. So I apologize for that. I didn't make the rules. If I did, I would change it probably. Okay, so this like steps here for finding extrema. If we take everything that implies the first derivative and replace with second derivative, we're basically talking about the steps for finding concavity. So if we need to find intervals of concavity, that's the procedure. Okay, that's not the second derivative test though. So I just wanted to point out, like, all the work we did the first half of the class, we get the concavity bits for free, effectively. Okay, a question like this is very common though. Identify all the intervals where the function's increasing, decreasing, identify all the extreme values, identify all the inflection points, and identify the intervals of concavity. Okay, we haven't talked about all these words yet, but increasing and decreasing, we can look at F prime, right? Concavity, we can look at F double prime. Extrema, we can use all of that information about where the function is increasing, decreasing, and specifically changing from increase to decrease or changing from decrease to increase. That information will inform where we have extreme values. So extrema is the fancy word for maxes and mins combined into one word. Okay, what is an inflection point? Inflection points are defined slightly differently depending on the textbook, and I think this is a slightly different book from ours, but I think this definition is a little easier to understand than what the book says, though. So inflection points are kind of like critical points for the second derivative, but they're kind of not. A critical point is defined in terms of where the derivative is 0 or undefined. An inflection point is defined in, does the concavity actually change? Okay, so the critical point, we can have a critical point even if the increase decrease doesn't change. We only have an inflection point when the concavity actually changes. I don't know what didn't come through because my computer just said my internet was unstable. So I might just say that again. You can have a critical point even if the increase decrease doesn't change on either side. But you only have an inflection point if the concavity does change. Okay, and the idea of where the graph has a tangent line, that's just helping us say that like a point of inflection really should be in the domain. Our book is a little unclear on that, unfortunately, but we won't test you on something that requires knowing that exact detail unless we specify exactly what we mean by whether the point should be in the domain. Okay, so I guess we call this the second derivative test for concavity, then it's pretty much directly analogous to the first derivative test for increase, decrease. Yes, Nasser, what is your question?
So for the critical points, we can have a critical point between two increasing. Like if the function is increasing, then it's like the slope is 0, like we have here. Yeah, exactly. So at -4, we can have that's a critical point, but it's not an inflection point.
Right. So an inflection point on this graph, where would the inflection points be? So let's grab new color.
At
There's an inflection
5.5.
point somewhere in here. It needs to be where the tangent line kind of crosses through the function. Is there an inflection point here? The inflection changes. The concavity changes from 0. Like straight line has a 0 concavity. And then here the second derivative is less than 0. Here the second derivative is greater than 0. Here the second derivative is less than 0. Second derivative is greater than 0. So this point actually is also an inflection point because the concavity does change there.
Okay.
So yeah, critical points can happen even if there's no change in increase, decrease. So the example here is -4 is a critical point, but the function's increasing before and increasing after. -4 is also an inflection point though, because this function happens to be concave down before and concave up after. It's not always common for critical points to be inflection points. So for example, here's a critical point. Is this critical point also an inflection point?
No.
Good. Here is an inflection point, but it's not a critical point. Okay. So just because you have a critical point doesn't mean you automatically have an inflection point. You have to just think about inflection points are, where does my concavity change?